Welcome to discussion 25. In today's discussion, we'll focus on section 4.7 on optimization. In this video, we will do an example where we find the closest point on a curve to a given point. So this is problem 6 from worksheet 12, and it says to find the point on y equals 2x squared that is closest to 8 comma 1 over 4. Okay, so I want to begin by identifying what it is that we're trying to maximize or minimize. And in this case, we want to minimize something because it says closest point, and we want to minimize a distance. Okay, so let's draw a picture. So I'm going to draw some axes, and I'll draw the graph of this. This is a parabola. The leading coefficient is positive, so it's going to be upward facing. And the vertex of this is at the origin. So we have this upward facing parabola. And then 8 comma 1 over 4 is somewhere over here relative to the parabola. 8 comma 1 over 4. I know it's going to be way to the right because if I plug 8 into the parabola equation, the y value is going to be huge. It's going to be 2 times 8 squared is 64. That's 128. So on the parabola, when x is 8, the y value is way up here. It's 128. All right. So I want to know the point on this parabola graph that's closest to the point 8 comma 1 over 4. So for right now, I'm just going to label some point. I'm going to draw a line, straight line connecting them. And I'm going to label, because I don't know the coordinates at this point, I'm going to assign variables and call it x comma y. Okay, so at this point, we are ready to write down our objective equation. So our objective is an equation for the quantity we want to optimize. We want to, in this case, minimize. And in this problem, we want to minimize distance. So I'll write d for distance. And we'll use the distance formula between 2 points. So remember, the distance formula gives us a big old square root. And then within that square root, we do the x coordinates subtracted, and we square them. So that'll be x minus 8 squared. And then plus, then we square the y coordinates being subtracted. So y minus 1/4 being squared. And as we've seen in optimization problems, right now the objective is in terms of 2 variables on the right-hand side. There's an x and there's a y. So we need to come up with another equation, which we call the constraint. That'll let us rewrite the objective in terms of 1 variable, so then I can, in this case, minimize it. So at this point, I want you to pause the video for 6 minutes to try this question. 4, 3, 2, 1. Pause it for 6 minutes and try this question on your own. Alrighty, so hopefully you did that. Hopefully you paused it and tried it. So I'm going to start to talk about it. In today's discussion videos especially, I'm going to push the pace a little bit. As I talk through it, I'm going to go more quickly than I typically would. So I'm really going to trust that you spent those 6 minutes trying the question. So some of the steps that I take, hopefully you've already done, and the pace won't seem that fast because I'll be doing some of the steps you already did, hopefully. Okay, so for the constraint, so I know this point x comma y is on this graph, and its equation is y equals 2x squared. So that's my constraint. So I can take that and I can plug it into my objective to get d equals big square root, and then it's x minus 8 squared plus, and let's plug in for the y. We'll get 2x squared subbed in, minus 1 over 4 squared. Okay, I am going to simplify the inside of the square root a little bit. I just think it's going to make it easier to take the derivative. So we got this big square root, and if we square each of these things, x minus 8 squared is x squared minus 16x plus 64. The next thing squared will be plus 4x to the 4, and then we'll get minus x squared plus 1 over 16. All right, and I can combine some like terms. I also notice the x squareds cancel. Okay, so what I'm left with is 4x to the 4 minus 16x, and then we have that plus 64 plus 1 over 16, and then this whole thing being square rooted. When I take the derivative of this, that plus 64 and that plus 1 over 16 won't really matter. So I'm going to just leave it as it is. I'm not going to bother with getting a common denominator to add them together. Okay, so at this point, this is pretty simplified. So we are ready to take the derivative. So we can find critical critical numbers, and then test them to see if they give us maxes or mins. So I have a square root of some complicated stuff. I'm going to show you two ways to handle this. So method one, I'm just going to call optimize this function as it is, d. All right, so we're going to do the derivative. So the derivative. So we would rewrite this whole thing as being this stuff to the 1/2 power. So the 1/2 would come down, and then we'd have all that stuff, 4x to the 4 minus 16x plus 64 plus 1 over 16 to the negative 1/2 power. Then we do chain rule, and we multiply by the derivative of the inside, which is 16x to the 3rd minus 16. Okay, and then let's simplify this a bit. So I can bring that 1/2 power to the bottom and the 2 to the bottom. And the 1/2 power I can rewrite as a root. 4x to the 4 minus 16x plus 64 plus 1 over 16. And then on the top, I can put that 16x to the 3rd minus 16. So that's my derivative. I now want to know, when is this equal to 0 and when is it undefined? So my derivative equals 0 when I need the numerator to be 0. So that happens when 16x to the 3rd equals 16. So if I divide by 16, x to the 3rd equals 1. And if I cube root both sides, we get x equals 1. So now I got to think about, when is this undefined? So this would be undefined when the bottom is 0, but there's actually kind of a nice trick there. It'll turn out the bottom never is 0, so my derivative's never undefined. Since, remember, the square root term that I have on the bottom, that was this distance. That was the distance between these 2 points. But just by looking at the picture, the distance between those 2 points is never going to be 0. It's always going to be something positive. Okay, so that's going to be the trick. So the square root of that stuff is the distance. And the distance is never equal to 0. It's always positive. All right, so at this point we have our critical numbers. It's just 1. We now want to test our critical numbers. And we saw in lecture that there's 3 ways to do this. So the 3 ways, let's recap those 3 ways. Okay, so the first way is I call this the closed interval method. So we use the closed interval method and the extreme value theorem. Okay, so the extreme value theorem says on a closed interval, as long as my function is continuous, it will have an absolute max and an absolute min. Okay, the second way was to use the first derivative test plus some justification. And the third way is to use the second derivative test. The second derivative test plus some justification. Okay, so I'm going to summarize some key points about these methods. So with method 1, it only works when we have a closed interval. If my interval for my variable is open, I can't use it. And it finds both the absolute max and the absolute min. So with the other 2 methods, we can use them on both open and closed intervals, but they will only find one of the absolute extreme points. So it'll either find the absolute max or the absolute min, but not both. So for example, if I'm doing an optimization problem that's asking for a max, and I decide to use method 2 or 3, and that gives me a min, it typically means one of 2 things. Either I did something wrong in my computation, or it was actually a closed interval, and I needed to do the closed interval method to find that min. So in our problem, the interval for our variable was x. Remember, we had written our function d in terms of x, and x just represented the x-coordinate of a point on this parabola. Well, the x-coordinate could be anything. So the interval for x is -∞ to +∞, and that's an open interval. So we're either going to use method 2 or method 3 to test our critical number. All right, so let's do this using method 2. Let's use the first derivative test. plus some justification. So the first derivative test is where we make a number line and a sign chart for the first derivative to see where is our function increasing, where is it decreasing, so we can classify our critical numbers as maxes or mins. All right, so I'm going to make a number line. We put a tick mark at 1 because that was our critical number. And then I need to keep track of the factors that showed up in my derivative. So on the numerator, we had 16x cubed minus 16. On the denominator, we had 2 times the square root of some stuff. I'm just going to put a squiggly line. Okay, so those together will form my derivative of d. And then based on d, I can say something about the original function. Okay, let's separate out some rows. Let's separate out columns. Okay, with 16x cubed minus 16, if I plug in something bigger than 1, it's positive. And it's negative if I plug in something smaller than 1. We've already seen that the square root of this stuff represented the distance. And that distance was positive, looking at my picture. So this 2 square root term, this is going to be positive everywhere. Okay, so this makes d prime a positive, and a negative divided by a positive, that is negative. So when d prime is negative, d is decreasing. When d prime is positive, d is going to be increasing. Okay, so typically this number line would tell us that we have a local min at this point. But when we are doing this optimization problem, we need to justify why this is an absolute min. So we do that in the following way. Since d, our function, is decreasing for all values of x less than 1, and it is increasing everywhere after that for all values of x that are greater than 1, the local min at x equals 1 is, and it might help to visualize this with a picture. So if I label 1 here, my function, d, the distance function, is decreasing the whole way until I get to 1. And then it's increasing the whole way after that. Because of that, this local min has to be an absolute min. This is an absolute min. And that is what we wanted. So the last thing I got to do is I have to make sure I answer what the question wanted. So answer what the question wanted. And the question wanted to know, where is that point? And right now I know the x coordinate of the point. I know it's 1. So to get the y coordinate, let's plug this into our parabola equation, y equals 2x squared. So we get 2 times 1 squared, which is 2. So my point, my closest point is 1, 2. And that's our answer. Turns out that is the point on this parabola when x is 1 and y is 2. That is closest to 8, 1 over 4. Alrighty, so I mentioned earlier that to take this derivative, I did this by optimizing d. I just took the derivative of the square root function. There is a quicker way though, and I want to show you that quicker way. Okay, so method 2 for handling this derivative is to optimize d squared. Let me write that d better. Let me write it like this so it looks a little bit more like a d squared. Okay, so remember what d was. So our function for d was 4x to the 4 minus 16x plus 64 plus 1 over 16, that whole thing being square rooted. So the key fact about this, that's going to let me just square this thing and look at that, is the x value that minimizes this thing, that minimizes the square root of some stuff, if that stuff inside of the square root is greater than or equal to 0. In this case it will be, because this square root thing is representing a distance, and from my picture I can see that that distance is always positive. Okay, so if that happens, the x value that minimizes this whole square root thing will also minimize it'll also minimize the square of this thing. And when you square this thing, you just get the stuff inside. Okay, I'm going to put a little thought bubble around this. All right, and now we want to square both sides. Okay, so when we do this, we will get d squared on the left. And on the right, we'll get 4x to the 4 minus 16x plus 64 plus 1 over 16. Okay, and now let's take, now the square root's gone, and that's nice. Now let's take the derivative. So we'll take d dx of this. So when we do that, on the left, we get the derivative of this d squared function. I'm just going to write d squared prime. And on the right, that derivative is going to be 16x to the third minus 16. So we are now just going to treat the d squared like a function, like f or g, and we've gotten its derivative, and now we're just going to find the critical numbers of this function. Okay, so I'm going to put a dot, 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 because we've done some of this work already, and I'm going to just tell you what the critical numbers are. The critical numbers we get from this are x equals 1, and from here, I'm going to put another dot, 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 because from here, it's going to be the same steps as in method 1. I'm going to put an exclamation point. So essentially, we would just be doing sign chart stuff with this derivative function. So notice we don't have that square root anymore on the bottom. So that's going to be simpler to work with. And when we do that, we'll get that x equals 1 corresponds to a min. All right, and then we could find the y value by plugging it in to the parabola equation as we did above, and it's just nicer computationally.